Today I am going to discuss groups of order 4. It will be found that only two types of groups of order 4 are possible. Let us consider a group G whose group elements are identity A, B and C, and a binary rule for composition, that is, rule for combining any two elements of this set, is defined. If this is a group, then the multiplication table must obey the rearrangement theorem. No element in any row or in any column will be repeated. Let this be a multiplication table. These are the first elements to be considered and these are the second elements. So the first row will be E, A, B, C, because if E is the identity, element, then the first row and first column can be immediately written down. A into E is A, B into E is B, and so on. I have written here three such partial tables because if we consider this row is to be filled up with E, B and C because A is there. Now we can place E under A or under B or under C. We have three possible ways: placing E here or here or here. Hence I have taken three tables. Now let us consider this space, and this is to be filled with B and C because A and E have been already taken. So under B we have to write C, obeying rearrangement theorem, and here we have to write B. Similarly, in this column we have to write C here and B here. In this way, this part can be filled up with B and C. C is not allowed here, therefore here we have to write B and here C. Similarly here C, B. These are the three possible cases: 1, 2 and 3. Now let us examine. Let us start with 1. In this row we are considering 1 first. In the third row at this place we have to write either E or A. I have done it here. I have taken case 1. Here we have written E, then CB, and here CB. Now this place can be filled with E or A. If we fill it up with A, then we have this case A. If here we write A, then here we are left with only E, and here B, C, A have been taken, therefore we must write E here and A here. This is how this table is filled up, and in this case, if we write at this position, if we write E, then here we have CB. At this position, if we write not E, we are left with A and E. Yes, if we write E here, then here we have to write A, and here A, and here E. This is the other possibility. We note that here E appears diagonally, but here E does not appear diagonally. These two tables are different. Now, in this case, we see that A combined with A gives E. Simply we can write A square is equal to E. And B, similarly B combined with B, that is B square is A. B square is A. This means that B to the power 4, B taken 4 times, will give you A square, and A square is identity. So you have B to the 4 is E, identity. A square is E. And what is B to the power 3? B to the power 3 may be taken as B square combined with B. B square is A combined with B gives you what? A combined with B gives you C. Therefore, C is B cube. Thus, the 4 elements of G, that is E, A, B, C, these 4 elements can be written as follows. E can be replaced by B to the power 4. A can be replaced by B square. Here we find A is B square, B is left as it is, and C is written as B to the power 3. So we note that B is the generator of all these elements. Different powers of B up to B to the power 4 constitute the whole group. The whole group G is like B square, B cube, and B to the power 4. Any group of this type, X square, up to X to the power N equal to E, any group of this type is called a cyclic group of order N. It is written as Cn. So this group can be regarded as a cyclic group of order 4 with B as generator. Here X is the generator. Here B is the generator. And we also note that AB, you also note that AB is C, AB is C, and this is also equal to BA equal to C, AB equal to BA. Similarly, BC will be found to be equal to BC equal to CB, AC equal to CA, and so on. So this group is commutative. All commutative groups are called abelian groups. Abelian groups. Abelian group, and this name is derived from the name of the mathematician N.H. Abel. All commutative groups are called abelian groups. Now come to this case. Here we find that because of this diagonal position of E, we find that A square is identity, B square also is identity, C square is also identity. And by no means we can arrange these, we can recast these elements in this form. By no means we can do this. Therefore, this is not a cyclic group. This is a cyclic group, but this is a non-cyclic group. But this is abelian because we find AB is equal to C, also BA is equal to C, CA equal to B, and AC equal to B. Thus it is commutative. Non-cyclic but commutative. Commutative means abelian. So both the groups are abelian, but one is cyclic and the other is non-cyclic. These two cases are only possible cases with group of order 4, because if we try with these two cases 2 and 3, we will arrive at the same conclusion. There can be only two types of groups of order 4. Both are abelian, and one is cyclic, the other is non-cyclic. Let us now come to actual examples of point groups, symmetry point groups. The point groups C2v, C2h and D2 are non-cyclic abelian groups. C2v is this 4 elements identity C2 sigma v primed. If you square each of these elements, you will find E. Here also E is C2 sigma h and I in case of C2h, and in case of D2 E is C2 C2 prime 1 and C2 prime 2. All these are of the second type, non-cyclic abelian groups. Non-cyclic abelian groups are called Klein's 4 group. Klein's 4 group. There are 3 point groups of Klein's 4 group type. And there may be other abstract groups which belong to this category, but in case of point groups with which we are interested, we have only 3 such groups, C2v, C2h and D2. It will be found later when we come to representation theory of groups that these 3 point groups have the same body of the character table. The character tables differ in the basis sets, differ in Mulliken symbols, but the main body of characters is the same for all these 3 groups. So with this, I conclude today's discussion. Thank you very much for watching this video.